Hi, today I'm going to talk about multivariable functions. Let's first define it. If a domain of a function is Rn, by Rn we mean this set, this Cartesian product n times, and the range is R. Okay, by a multivariable function, we mean a function whose domain is Rn and the range is R. Then we call it multivariable or n-variable function, and we denote it by this symbol. Okay, some examples. Here is the usual one, the one you know already. One variable functions. You have a knowledge about the one variable functions. You know how to take limits, how to derivative, how to determine continuity, how to take integrals. You know almost everything about one variable functions. Afterwards, we investigate multivariable functions. For instance, two variable functions, which is our mostly interested in, and three variable functions, and the general formula, namely n variable functions. Yes, as I said before, you can see in this note, we deal with mostly two variable functions. Okay, here is a diagram for two variable functions. As you can see, the number of variables are 2. Our domain is R2. Okay, so the domain of the plane, D, this set. Okay, this set is a domain of R2. We shortly call it plane. Yes, and the range, as you can see, is the real axis, and f is a function mapping the point x comma y to the value f of x comma y. Yes. Okay. Let's define it formally. Let's consider a two-variable function f, and the domain of f is written in a set notation. This notation, and this notation denotes the phrase is the set of, and a vertical bar denotes the phrase, such that domain f is a set composing of the points x comma y, such that property of x and y. More explicitly, let's provide an example. Find the domain of the function logarithm y minus 2 times x, and sketch the graph of domain in xy plane. Okay. As is known, this part must be positive. So we have an inequality y greater than 2 times x, and our domain composed of the points x, y, such that the second component must be greater than 2 times first coordinate. Okay. If this is an equality, but if it was as an equality, I mean, if it was like that, then the points satisfying this equality must be a line passing through the origin. Yes. And it's a question y equals to 2 times x, but we have inequality, and equality is greater than 2 times x, which means that this part, of course, the points on the line, we omit the points on the line. I mean, yes. Okay, we omit these points, but the upper place, of course, up to the x-axis, I mean upper, up in the points in the upper of the line, this line, is our domain. If this question was given like that, then it would be like that. Then our solution would be this place. Another example. Let's find the domain of such a function. Okay. In order to well define this function, then x and y must be greater than or equal 0. This means that our domain is the first quarter of the xy plane. I'm in the place and the painting by blue. Another example, again logarithm, and this part must be positive, which means that x squared plus y squared smaller than 1. If it was equality, then this equation, I mean x squared plus y squared equals to 1, this equation determines a circle. Yes, like that. But in our case, in our case, we have not an equality, we have an inequality, and the sign of inequality like that. This means that our points inside points of this circle, but the points on the circle doesn't belong to the domain of the function f. Yes. Some diagrams. This is our solution. If it was smaller than or equal, we have such an figure and other possibilities. Okay, another example. We have an polynomial. As you know, the polynomials are defined on the all points entire of xy plane. That's why our solution is the r square itself. Yes, as we wrote like that. Another example, we have a rational function y over x, and in order to well defined the function f, it has to be x different than 0. Then our solution is this set, and we may show it in the xy plane R2, or we say xy plane. Yes, all points excepting the y-axis. Yes, similar are the problems, and you can solve these problems by yourself. Okay, and limit and continuity of multivariable functions. And in this part, we will concentrate the mostly on limits of two variable functions, because the arguments can be extended to functions with arbitrary variables. Okay, let's recall the limit of one variable functions that you know already. Y equals to y, f of x be a one variable function. Okay, this limit exists if and only if the approach from the left side to A and from the right hand side to A must be exist and must be equal. Okay, uh, in the special case one variable function, we have only two directions, which means that the determining limit of at any point A is simple, but in our case is a bit complicated. Let's explain now. Okay, let f z equals to f of x comma y be a two variable function, and the limit of f at the point a comma 1 is denoted by this symbol. This is important. Please keep this symbol, I mean the equation 1 in your mind. And to solve equation 1, we have two methods. The first one is the Cartesian coordinates method, and the second one is the polar coordinates method. Okay, we start Cartesian coordinates method. Let's consider the following limits. I mean this limit. This notation says us that the limit of the function f at the point a comma b, sorry. Okay, to determine it, we have following steps. Please pay attention on this part, which is very important. Okay. By the way, the function f can be undefined at the point, which is not important. The point is if it has limits at the point a comma b, not defined at this point. Okay, first step. Firstly, if the limit exists, then it is independent of the approaching side to the point a comma y. Firstly, we perform these two steps. I mean the step equation 2 and equation 3. As you can see, firstly, we approach from the axis y, and secondly, we approach from the axis x. If those are different, then we say it limit does not exist. Okay. If those are equality, please have a look here. If those are equality, we need to approach to the point on a different way. Namely, if those are equality, it doesn't mean that the limit exists. I mean, the equality of these two limits does not say says us that the limit exists. So, if those are equality, you would choose a curve which includes the point a comma b. Then approach to this point on this way. We obtain another limit, let's say 4. If the result is of the limit 4 is different than 2 and 3, then we say its limit does not exist. Otherwise, namely all are equal, we say limit maybe exists, maybe not. Namely, the Cartesian coordinate method in this case doesn't say anything. Yes, this is the diagram of the step 4. As you can see, in a plane, let's say xy plane, to a point, to any point, a comma b, you can choose infinitely many directions. That's why it's not possible to check every direction. So, namely, the Cartesian method, let's put a note here. Let me write here the Cartesian method by the Cartesian method you can obtain non-existence of limit. However, you can't say that a function has limit. Yes, that is the point. Let's provide some examples. Let's solve this limit. The point is origin. Yes. We are looking for limit at the point 0, 0, which is origin. And we have only one method, which is Cartesian coordinates. Okay. The first step, we approach in this way. Let's replace y with 0. Then we obtain this limit. As you can see, here is 1. Okay. Let's change the direction. First, we approach on the axis x. We replace x with 0. Then we obtain this limit, which is equal to 0. And those are different, which means that the limit does not exist. Another example of limit at the origin. If we replace y with 0, then we obtain this limit, which is 1. And changing approach, namely replacing x with 0, we obtain this limit, which is -1. And finally, we can see that those are different. Obtaining the limit does not exist. By the way, I should say that the function f of x comma y in this example is not defined, and the previous example as well. The functions are not defined, which is not our interest. We deal with if exists limit or not. Okay. Another example. This example is different because the function is defined at the point 0, 0, and we are looking for a limit for that point. Okay. Firstly, we approach through the axis y. If we replace y with 0, then we obtain 0. And similarly, we again obtain 0. If those are equals, then we have nothing. If those were different, then we would say the limit does not exist. But otherwise, if those are equal, then we can't say anything. So we have to, we can't say anything at the moment. So let's change the direction. Yes, our point origin, and let's draw an plane, xy plane. Okay. Through the origin, there are infinitely many curves. So we choose, for example, a parabola y equals x squared, or we may choose a line, let's say y equals x, or a cubic curve, let's say y equals to x3. Yes, you can choose infinitely many curves. Let's choose the first one. Yes, we approach the origin on that line. Okay, which means that we replace y with x on this function. Then we have such a limit, x squared over x squared plus x squared. Then we have the limit 1 over 2. Okay, these limits are different than those. So we have a non-existence of limits. Here I have to write something. Okay. In order to have a limit, it has to be independent of approaching. Yes, but just a minute. But by the Cartesian coordinates, it is not possible to check it because there are infinitely many ways. So this method, as I write before, this method, by this method you can obtain non-existence, just non-existence. By this method you can't say, you can't obtain, you can't solve the case that a function has a limit. This is important. Okay. Another example, we have a trigonometric function, sine of xy over y. Okay, and our point is 0, 0,1. Okay. Yes. Firstly, this approach, we replace y with 1. We have sine of x, and we have the limit 0. Another approach, we obtain again 0. And this means that we have nothing at the moment. The limit may exist, the limit cannot exist. Okay. So after this stage, we have to choose a new direction, passing through the point. Okay. If we choose a line passing through the points 0, 1, yes, you know, this line pass through this point. Okay, we can choose this line, and we can solve. So by the way, we have to replace y with x plus 1, and we have a continuity function, and the limit is 0. Okay, we have all 0. 0, first approach, the second one, and the third one, and those are all 0. So the limit maybe exists, but maybe. So we have not a certain result. We are not sure, which means that the Cartesian method doesn't work in this case. Another example, we have a function e x minus y, and our point is 0 logarithm 2. Yes, at the first this approach, and we obtain 1 over 2, and similarly we may obtain again 1 over 2. So we have to choose another direction. Yes, we may choose this one. There are infinitely many options. We choose only one among them. So if we replace y with x plus logarithm 2, and we solve this limit, which is easy, again we obtain 1 over 2. So similar to the previous example, we are not sure for this example. Yes, we have a note. We have two options. If f is continuous, then yes, we plug the point into the function directly. If it is not continuous, but it's possible to make some simplification, then make it then plug the point into the function. Okay. If the function f is not continuous and it's not possible to eliminate this discontinuity, so we need to use the Cartesian coordinates methods and the polar coordinates methods. Let's provide an example. Okay, we have such a function which is continuous because we have polynomials and trigonometric functions which are already continuous, and we have this result. Another example, a rational function, and which is continuous at this point. This function is not continuous when this equality satisfies. But the point doesn't satisfy this equation, which means that the function is continuous on that point. And the limit exists 5/6. Okay. Another example, determine if the following limit exists or not. If they do exist, give the value of limit. Okay. Clearly, this function is not continuous on this point because this function is not continuous provided x equals to plus or minus y. So at the first stage, easily you can say this function is not continuous, but as in this note, yes, to make some simplification, you may obtain indeed the function is continuous on this point. Yes, after some factorization, you obtain this limit. Yes, finally we have a certain method, polar coordinates method. By using this method, you solve almost all the problems, limit problems. Okay, let's explain. When you use the Cartesian coordinates method, you can conclude that it's not too effective and certain. And therefore, we prefer to use polar coordinates methods. This method is more effective. So let's explain it. Consider this limit, the limit 1. And we transform the Cartesian coordinates to polar coordinates. And x, y, r, theta. By using these equations, x equals to a plus r cosine theta, and the y equals to b plus r sine theta. Let's explain this method step by step. Okay, first we use, by the way, please pay attention. Yes, if your point is a, y, so you wrote here a and b. Okay. First, as a first step, use the equation to transform the variables and take the limit as r goes to 0. We have two options. If the result depends on theta, then we say the limit does not exist. Otherwise, the result is independent of theta. Then we say the limit exists, and the result is a. Okay. So let's explain why r goes to 0. As you can see from these examples, from these equations, sorry. And we have a Cartesian equation, x minus a square plus y minus b square equals to r square. If x and y goes to respectively a and b, so we have this approaching. Okay, this is the justification why we take r goes to 0. Okay. Let's solve this limit using the polar coordinates method. You can see the point is origin, which means that you replace x with r cosine theta, y with r sine theta. After this replacing, you obtain cosine square theta. So, and the limit as r goes to 0, you obtain this statement, which means that the result depends on theta. Namely, as you change the value of theta, you obtain different values. Yes, it's clearly that the cosine square theta may take some values in this interval, and there are infinitely many possibilities. So this means that the limit does not exist because the result depends on theta. In order to have a limit, the result has to be a real number, independently the value of theta. Another example, our function is this, and the point is the origin. So we have to replace x by r cosine theta and y r sine theta. So after replacing, we obtain f equals to r multiply this mathematical statement. So if r goes to 0, then we obtain 0 independently the value of theta. No matter what the value theta is, we have the limit is 0. So we say that our limit exists and equals to 0. Another example, our function is this, and the point 2 comma minus 1. So for the polar coordinates, we have to replace with x equals to 2 plus r cosine theta, y equals to minus 1 plus r sine theta, which means that we have to use those equations. After replacing, we have r cosine square multiply sine theta. So if r goes to 0, then we have a limit 0 independently the value of theta, which means that our limit exists and the value is 0. Another example, our limit, our function is x over square root x square plus y square, and the point is the origin. So we have to replace with this transformation and we obtain cosine theta. The result depends on the value of theta, then we have not, then our limit doesn't exist. Yes, some another examples, and you may solve by yourself. Some algebraic properties of the limits. If two functions has limits L1 and L2 at the same point AB, then we have those properties, those algebraic properties. Okay, and the continuity of two variable functions. A two variable function is continuous at the point AB if and only if f has to be defined at that point, the limit has to exist, and the limit equals to the value of the function f at the point AB. If at least one does not hold, then we say f is not continuous at that point, or shortly discontinuous. An example: show that this function is discontinuous at the origin. The function is defined, as you see. So the point is the limit, the function f has limit at the origin or not. Yes, the first item holds. Good. Let's check the limit. And we may use the Cartesian coordinates. We mean firstly this approach, and we obtain a limit 1. And second approach, we have limit 0, which means that the limit doesn't exist. If the limit doesn't exist, so we have discontinuity. Okay, let's solve this example. We determine if it's continuity or not at the point 0, 0. Okay, the function is clearly defined at the origin. Okay, let's check it has limit by using the polar coordinates. Since our point is origin, then we have those transformation equations, and if we replace with the values x and y into the function f, then we obtain r 4/3 cosine theta multiply sine theta. If r goes to 0, then we have the limit as 0, independently the value of theta, which means that our limit exists and the value is 0. The limit exists and its value is 0, and also the function takes the value 0 at the point origin, which means that our function is continuous at the origin. Another example. Okay, the function is defined at the origin. The first item is good. The second one, we may observe the limit by using Cartesian coordinates. So the first two approaches, you can check by yourself, are 0. So we need to choose a new curve. Let's choose a parabola passing through the origin. And if we replace y with x squared, we obtain 1 is a constant function. And of course, the limit is itself. So 1 is different those limits, which means that the limit does not exist. So our function is discontinuous at the origin. Okay, partial derivative. The partial derivative is to take derivatives of multivariable functions. In particular, we more concentrate for the two variable functions. Okay, let's define it. Let f a two variable functions. Okay, if this limit exists, then it's called the partial derivative of f with respect to the variable x. Yes, as you can see, the replacement or the change from the x direction. And we have these notations, which is very important. Keep these notations. Similarly, if this limit exists, then we call this limit the partial derivative of f with respect to the variable y. And you see the replacement, the change is on the y-axis. And our notations in this case are this. A note on notations. If you have a function of one variable, then the derivative is denoted as this symbol, or we denote it f prime. But for two variable functions, we have a curved d, like that. This is a new symbol. Yes. For a function f of two variables, f subscript x and fy are called the first order partial derivatives of the function f. An example. Consider the function x squared minus 2xy plus y squared and find these derivatives at point 1, 2. Yes, if you want to find this partial derivative, then you have to, at the moment, you have to solve these limits, which is simple. Yes, if we replace x with 1 plus h and y with 2, then you obtain this function, and its limit at the point 0 is minus 4. And symmetrically, if you replace x with 1 and y with k plus 2, you obtain this function, and its limit at point 0 is 1. Those are the values of partial derivatives. And another example, the function is defined by like that. So let's find the partial derivatives at the origin. So we have to solve these limits. If we replace x with h and y with 0, then we obtain a 0 function which has the limit 0. And similarly, again, we may obtain 0. Those are the simple calculations. So our partial derivatives are 0 at the point 0, 0. And by the way, we may obtain the partial derivatives without the formal definition, and let's explain it in the next video.